Hi everyone, this is Dr. Keller. It's good to have you this semester, and we are going to start our lecture series if you are interested in the lectures to accompany your readings in the book. And we're going to start with chapter 1 in the book. That's the chapter we're on right now. And it's an introduction to chemistry. A lot of the information you've probably heard a lot in this chapter, but it's just a good way to put us all on the same page and to just start learning about chemistry and some of the topics we're going to cover this semester. So first, let's talk about the nature of chemistry. But when we start there, we want to start with the definition of what chemistry is and what it studies. Chemistry studies two things. It studies matter, and it studies the changes in energy as matter undergoes changes. So let's write that down. Alright, and I'm already going to apologize for my handwriting on my iPad because this huge stylus and trying to write on my iPad without laying my hand down, oh my goodness, it's not easy. But I'm going to try my best to make it very legible for you. So let's go through the definition of chemistry again. Chemistry, the study of the composition of matter and the changes it undergoes. So what matter is composed of, and when it undergoes changes, what's the change in the composition from one substance to another? The second definition of chemistry is the study of energy and the changes it undergoes. And usually when we study chemistry, like I said before, we study the changes in matter mainly, but energy and how that accompanies the change in matter. So they really actually go hand in hand, what we'll see. What is matter, though? How do you describe matter? I always say that matter is stuff. So matter is not nothing, it is something. The technical definition of matter is anything that has mass and occupies space. So anything that has a mass and occupies space is matter. And chemists are interested in matter, what matter is composed of. We'll talk about elements and compounds later. And energy changes that accompany changes in matter. So how do we look at matter from a chemist's perspective? There's several different ways we can talk about this, but one we'll just kind of start with as an overview is the macroscopic versus microscopic views of matter. So what is macroscopic view? Macroscopic view describes the characteristics or behavior of a substance, or a sample, that is large enough that you can see it, you can touch it, you can manipulate it, you could weigh it out. So it's anything that's visible or tangible that we can see and hold. Microscopic is obviously the opposite. It's something that's very tiny, much smaller sample sizes. These are things like atoms or molecules. For example, if we were looking at this little gravy bowl here, we as chemists could look at that gravy bowl from two different views. Sorry, sales call there. Anyway, we could look at this gravy bowl from two different views. We could look at it macroscopically or microscopically. So if we were looking macroscopically, just with what we were able to see, we might say, hey, it's a gravy bowl. It's got a curved shape around the body, and it's hollow on the inside. It has a handle. Of course, that's just describing the shape itself. We could also say it's shiny. Maybe if this was a color picture, we could say it was silver in color. We could say that it had a substantial weight if we weighed it, things like that. If we looked at the microscopic view of this, we might go in the lab and analyze maybe some of the material that it was made of. We might say, well, this is a silver gravy bowl, not silver in color, but silver in the element that it was composed of. And this brings us to kind of the physical property of silver. Maybe the silver tarnishes easily. That would be a chemical property of that substance, and we'll talk about the properties in a second. But what if this wasn't a silver bowl? What if it had several elements that came up when we analyzed it? What if it was stainless steel? A stainless steel bowl, when a chemist analyzes it, has several different metals it's an alloy that are mixed together. There's a heavy percent of chromium, which gives it the stainless steel properties, because chromium, when it oxidizes, it's a kind of a thin, invisible film, versus when iron let's say, oxidizes, it would be more rust, like red-like and powdery. When silver tarnishes the silver sulfides and oxides, it's this blackish gunk on the top. So the chromium in stainless steel gives it the appearance that it's not oxidizing and cuts down oxidation. Of course, stainless steel would also have iron in it, which is very, very strong. Nickel, carbon, molybdenum, titanium. It depends on the stainless steel we're talking about. But those are two different types of material, a silver gravy bowl versus a stainless steel gravy bowl. And some people probably own more than one gravy bowl. They probably get the silver one out when the special guests come over, maybe on Thanksgiving or Christmas. And they probably keep the stainless steel one out maybe every day, like a lot of our silverware versus flatware. And the reason is these different materials have different properties. Silver tarnishes easily, whereas stainless steel, hard oxides, you can wash it in the dishwasher at high temperatures, right? You can use it with acidic foods over and over again, or I should say more acidic foods. And stainless steel, very strong, very durable for daily use. So these are just some examples. If we look at the microscopic view, if we got different analyses on what it was composed of, we would know that there would be different chemical properties because of the different compositions. And this brings us to the next topic in Chapter 1 that we're going to discuss as a kind of primary overview, and that's the scientific method. The scientific method, describes how chemists solve problems, or how scientists in general will go about solving problems or understanding more about a problem. So let's first talk about how we solve problems. If you have a problem that arises like, I wonder how to make a metal that looks like this really nice silver, but it doesn't oxidize as easily, and it's very durable and strong. What type of metal or metals should I combine? So that's just one example of a problem that's been asked and that's been answered. So how do we solve these problems? The first thing we always do when we want to solve a problem intelligently is we collect facts or data that are relevant to the problem. We just don't start trying to put things together like, hey, I think I'll take whatever metals I find and I'll mix them and try to make a really strong alloy. We collect facts or data about different metals before we start mixing them to create a new alloy. By the way, we'll talk about this in a second, but facts, things that we know, are sometimes referred to also as laws in science. The other thing we do is when we're collecting our facts and our data to solve a problem, we might have a problem in itself trying to figure out what data is valid or how to come up with a place to start. So a lot of times people will use carefully designed observations and experimentation in order to solve their problems. For instance, if you're trying to create a very strong alloy that doesn't oxidize easily and it's pretty like silver in color, you're not going to grab every piece of information available on every metal to start. That's information overload. Instead, you will look for certain properties that you're interested of different metals. For instance, we know that iron is very durable, very strong, so you would look maybe to that. You might look to other metals for color, oxidation state, if they're oxidizable easily or not. So those are just things. You're not going to pick out everything. You're going to hone in on things that are important to your problem. The next thing you probably do is you probably formulate a hypothesis that accounts for the data that can be tested further. A hypothesis, when I was growing up, we learned that it was called an educated guess. But a lot of scientists don't like the word guess because it makes it imply that you put no thought into it, even though the word educate is in front of it. So another way to describe a hypothesis is to call it a tentative explanation of the facts that can be tested further. And we'll talk about that in a little bit. But basically, when you formulate a hypothesis, when you have a problem to solve, usually in the back of the mind, you've got maybe some explanation of understanding what the problem is or how you're going to solve it. That's what a hypothesis is. A hypothesis is a tentative explanation of the facts that can be tested further. So you have to be able to test it. Like, for instance, I believe that iron would be a very good component in a stainless steel or in a stainless, or I don't know, a non-oxidizable alloy, because it's very strong. And I'm going to test the mixtures of different metals that are more silver in color with iron to see if it helps strengthen that metal. I don't know, I'm just making this up. But hypotheses are your tentative explanations, or your educated guess, if you will, of the facts that you already have at hand to solve the problem that can be tested further. Important part there. What do you do after that? The next thing you have to do after you kind of have an idea of what tests to do, what the problem might be, is you go ahead and you run the experiments. So you plan to do additional experiments to test your hypothesis. So then I would start mixing my different metals together in an educated way to produce different alloys, maybe with iron in it, or different amounts of irons and other metals. And I would go one metal at a time. I wouldn't try to change everything at once. And I would do those experiments to test whether or not they validate the hypothesis or they do not validate it. If it turns out you have formulations, or you're doing some experiments and they're not really validating your hypothesis, they don't really lend to the explanation you gave to solve the problem to begin with, then what you're going to do is you're not going to give up. Scientists never give up. We're constantly in the lab modifying our hypothesis and then running more experiments, and then if they don't work, we go back and modify our hypothesis. So it's constant experimentation based on facts and observations that are made before and during the experiments until we are able to solve the problem. Now, if you're more a visual learner, probably saying all of that or writing all that down, it helps to a point, but this graphic might help you a little bit more. This is kind of a visual of the problem solving in the scientific method. We said that if you have a problem, the first thing that you do, are you're going to carefully look for different observations and different facts. And I said those were called laws in the scientific world that relate to the problem at hand, to try to develop an explanation or a hypothesis as to how to solve the problem. Once you kind of have an educated guess or a tentative explanation that can be tested further using experiments, then you go ahead and you experiment what you think is the problem or what's solving the problem. And once the experiments are ran, you analyze the data, and if the data backs up the hypothesis, then you develop what's called a theory or a model. And we'll talk about that in a second. But what if the experimentation does not back up the hypothesis? Well, you go back, and maybe you'll need to look for more observations. Maybe you're like clueless, and you've got to go back to the beginning. My hypothesis didn't work. You've got to go back and look at the observations and laws at hand to make a new hypothesis. Or you could just go from experimentation and you could just redefine or develop your hypothesis from there. Re-experiment, and then if eventually the experiments support the hypothesis you made, you can then develop your theory. Theories are also called models, depending on kind of what you're talking about, as opposed to what the problem is. So let's come down here and let's define some of these words we've used, just so you know what the words are. It's very important to know the definitions of these words. The first one is observation. An observation, OBS for short, is a statement based on direct experience. A statement based on direct experience. For instance, silver, when exposed to oxygen and sulfur in the atmosphere, is known to tarnish. Okay, that's a statement based on a direct experience. It's an observation that can be made. The second definition we want to know is hypothesis. Remember, I said the hypothesis was a tentative explanation of facts that can be tested further. A theory is a well-tested hypothesis. The hypothesis was made, the experiments were run, they were tested several times and analyzed, and the experiments back up the statements of the hypothesis. So you can never prove by fact through experiment, but you can prove through theory that perhaps this is what's solving the problem. So theories are explanations, not facts, of what the general principles based on experimentation were. They can be modified over time. Theories can be modified or changed over time. Facts, laws, or facts cannot. For instance, what goes up must come down. That's not going to change on Earth because we have gravity. It's one of the laws of physics. What can change, for instance, is the model or the theory of what the atom is composed of. And we'll talk about this semester, but people didn't used to know what matter was composed of. And when someone theorized the atom, there were early stages of what the atom looked like. And there are models now that look very different based on more in-depth experimentation that's shown us more and more parts and more about the location, the charges, the masses of the subparticles found in an element. Can we prove the existence of these things that it's fact? No, a lot of those things we can't see. We see evidence of them through experimentation, and that's why they are theories, not facts or laws, and they can be modified or explained actually in more detail over time. Either one. And that brings us to our last definition, which is the law. So theories are explanations. They tell us the why, and laws are also known as facts, and they tell us what. Laws tell us what happens. Theories and models tell us why things happen or how things are arranged. So a law is a statement, not an explanation, of natural phenomenon to which there are no known exceptions. Okay? Like I said here, the theory answers the why something happens, and the law just simply states what happens. Okay? An object at rest will remain at rest until acted upon by an outside force. That's a law of physics. It's a fact. It tells you what happens. It doesn't explain why. That would be the theories. Alright, so let's look at some examples of questions pertaining to the scientific method and how to use it. So here's the first one. It says a clear colorless liquid is combined with a second clear colorless liquid, and the mixture is observed. Which of these is not an observation? So before we even go into the answers, let's talk about what an observation is. We are supposed to say which one is not an observation. Remember, observations, according to our definition, are statements based on direct experience. Can we taste it? Can we touch it? Can we look at it? So using your senses. Alright? So let's look at A. A says the test tube became hot to the touch. That's an observation. It's something that you can feel. You can touch the side of the test tube and notice that it gets warm. So that's an observation. That's not the answer. Let's go to B. The reaction is exothermic, releasing heat by the breaking of chemical bonds. Is that an observation? Some of you might know what exothermic is. It's a reaction that loses heat. But could you look at the two test tubes, or could you feel the two test tubes and explain what's going on just by looking or touching or feeling? Probably not. This is an explanation. It's an analysis or an explanation of what's going on. Maybe it's a theory, okay, or an analysis. But it's definitely not an observation. So the answer here, I'm going to go ahead and say it's B. We'll read the rest, and you'll see that those are observations as well. C, the mixture is cloudy. Yes, you can see if a mixture is cloudy when you look at it. And the mixture is white. So that's a color. It's something you can see again. Those are observations. So B is not an observation. It's an explanation. Which of these is a law? The next one. Which of these is a law? Let's talk about a law before we even go to solve the problem. So do you remember what a law is? It's a statement. Do you remember? It's a statement of natural phenomenon to which there are no known exceptions. It's not an explanation. It's just a statement of the facts. What happens, not why it happens, not how it happens. Remember that, well, I guess I just said it. Remember that laws tell you what, not why or how. Not how things are arranged or why they're doing something that way. So let's look at these. Which of these is a law? I just made a mess. Okay, let's go back. A. It has been discovered that atoms consist of particles called protons, neutrons, and electrons. Okay, that to me seems, and this one's hard, so that's why I'm doing it for you, and the book does an example like this too. This is a model. It's a model. But because it's telling you how the atom is organized, what it's consisting of. Subatomic particles, which we'll talk about this semester. But it's not really just a law, a statement of a fact. In fact, the other reason we know it's a model is because experiments led us to understand that we've theorized that matter was made of particles called atoms, and there are subatomic particles inside of them. So that one's hard, but I will tell you it's a model. Okay, let's look at the next one. If you thought that was a law, let's read the next one. There's probably one that's more clearly a law here. This is actually a theory, also known as a model. B. Experimental evidence finds that iron metal is composed of iron atoms. Once again, experimental evidence finds. Where were the laws located on that flowchart? At the top, not after experiments. So, once again, this is a theory. This is a finding or a model. So, it's a theory or a model based on experimental evidence. C. Atoms can form chemical bonds by sharing electrons. To me, that's a statement. It's kind of telling me how. Not a statement, but it's telling me how something occurs. It's saying if I have these atoms, they're going to form a chemical bond by sharing electrons. It's more of an explanation of how a bond is formed. Remember, an explanation, how or why, is a theory or a model. Okay, so let's look at D. It says the volume of a gas increases with increasing temperature. Well, that doesn't sound like an explanation at all. It sounds like just a fact. The volume of a gas increases with increasing temperature. Fact. That is a law. And there are no known exceptions to this too. If you take any gas and let's say you put it in a balloon, and you put it near a very, very hot fire, that gas is going to expand or increase its volume, right? As the temperature increases. It doesn't matter what the gas is. This is something that we observe happening in nature. It's a statement of natural phenomenon with no known exceptions. Notice it doesn't explain why the gas increases size or volume. It just says that it does. That's called a statement, not an explanation. All right, so D is the law. You just state the facts. All right, let's look at the last one here. It says the statement, an atom consists of a dense nucleus surrounded by a cloud of electrons. Well, gee, I could actually draw a picture of that. Here's this little atom. It's got a dense nucleus, and then there's this cloud of electrons outside, and that whole thing is called an atom. What did I just do? I drew something. It's a model, right, of the atom. And models are the same thing as theories, right? So it explains why or how something occurs, and how the atom is organized is an explanation based on facts, or analysis of experiments, So it's a theory. I hope that helps. The main thing that people really get messed up on is the difference between a theory can't write today. A theory and a law. So, one more time. A theory is an explanation of why something is the way it is, or why it behaved the way it did, or how something is set up, like in an atom. A law just says what is happening, not why. This is a statement. This is an explanation. All right? Okay. This is the first part of our lecture. We're going to look at the second part, and we're going to talk more about matter and how it's arranged and some of the properties of matter.